Good morning, college physics students. This is class for Monday. What is today? Monday, May 4th. We got a test this week on Thursday, 1 o'clock. There's a practice test on Wiley Plus. Once again, it's going to consist of, your grade's going to consist of two portions. Your grade on getting the answers on Wiley Plus, and also the submission that you're going to do within 24 hours of showing your work. I graded that pretty easily last time. That was the first try for that kind of format. When I teach this class in the summer online, I'm going to have video proctoring. There's a new product out that does video proctoring of tests. So I'll probably avoid this show your work part. It's to at least ensure that you're doing a little bit of physics. You know, this is a class about physics and thinking and being creative. It's not a course about finding answers on the internet. Finding answers on the internet is not a skill you can get paid to do, because anybody can do it. Anyway, I'm going to be much more rigorous in my grading of the show your work part, and I thought I'd show you what I'm talking about. This is a submission from one of our students. Here's problem number one. There's the information given. Here's an explanation of why the work due to mg is 0. Here's the work done by the pulling force. Here's the reason that the normal force is equal to mg, because the sum of the forces in the y direction is 0. And then here's the frictional force. The equations that this person's using are written out here, and then the information's plugged into them. Once again, here's the equations the person's using, information's plugged in. Several of you did a pretty good job at this, knew what showing your work means, and this is what it means. And if you don't have it laid out like this, you're not going to get very many points. So just a little warning. Okay, where are we? Well, nobody's asking me any homework problems, so let's move on to our last chapter. This is called thermodynamics. It's a study of heat, work, and internal energy. Remember, internal energy is the kinetic and potential energies of the atoms that are making up the system. So this is the rigorous formulation of the atomic theory, rather than just Democritus's speculation in ancient Greece that matter was made up of individual little packages. So let's define some terms here. So we always have a system. In this case, we're going to talk about the simplest thermodynamic system, which is just a collection of fairly rarefied collection, which is a gas of monatomic atoms. Monatomic atoms are atoms with just molecules with just one atom in them. So it'd be monatomic molecules. Monatomic atoms doesn't make sense. Monatomic molecules, which are like gases that are exist in that form at room temperature, things like helium, argon, all the noble gases. Hydrogen, oxygen, nitrogen, those common gases are all diatomic molecules. They have two atoms in them. Anyway, so we're going to just think about very simple systems, but the system can literally be anything. And if the system is a gas, especially, it can do work on the surroundings. It can expand and push against the surroundings. That does work. And we can also dump heat into the system, heat energy. And then there's some internal energy, U, inside the system. We could also do work on the system. That would be negative. Work done by the system is positive, and heat put into the system is positive. Heat added to the system is positive. Heat could be added to the system, and you could do work on the system, which would be negative. And the change in internal energy can be positive or negative. The internal energy can go up or down. Okay, so that's the basic idea of thermodynamics. This example right here encompasses one of the big ideas of modern man. It's the idea that makes our life so simple. Doesn't seem simple right now, but certainly much simpler than it was for people before this big idea. And here's the big idea. If I can take heat and put it into a system and get that system to do work, that's called a heat engine. And that's the idea that started the Industrial Revolution and continues to this day to make energy readily available to us and cause us to have to do a lot less work just to live day to day. Because you can take coal or oil or natural gas or what else? A nuclear reaction. You can use all those things to generate heat, put it into a system, which is called a steam engine, the most common system that's in use today. Take that heat and put it into a steam engine and have that steam engine do work. And the work that steam engine does for us is to turn electrical generators, rotate electrical generators and produce electricity. So this idea here is actually what gave rise to the science of thermodynamics in the 1800s. People were trying to understand what's the most efficient steam engine you can make. That is, how can I get the most work out of this system for the amount of heat that I put in? And we'll talk about that. Okay, I'm not going to be able to cover everything in Chapter 15. I'm going to cover what I can. There'll be one more assignment on it. Okay, so there's a set of laws in thermodynamics. And the zeroth law of thermodynamics is when two systems are at the same temperature, they're each in thermal equilibrium. By the way, the word adiabatic means that no heat can flow into the adiabatic means that Q is zero, the heat flow is zero. So if they're in equilibrium at the same temperature, if you put them in contact, they'll remain at equilibrium at the same temperature. The idea is that if you have two systems that are at different temperatures, heat will flow naturally from the high temperature to the low temperature. So that's the real basic law, most basic law of thermodynamics. It wasn't even stated, it was so obvious to people until it started to become a much more rigorous activity in theory, and they realized that they needed to state this law in order to make it complete. But now we get to the first law of thermodynamics, which came around before the zeroth law. Okay, so as I said, there's three kinds of energies we're dealing with here. the internal energy, remember that's in the case of a gas, that's just the kinetic energy of translation. It turns out for a monatomic gas, the only kind of energy you can have is just the kinetic energy of the moving atoms making up the gas. If they're diatomic molecules, they can also have rotational energy because they can rotate as well. You can't rotate up a single point of mass. But if you have a diatomic gas, it turns out that the internal energy will consist of the kinetic energy of the atoms plus the rotational energy of the atoms, just like in Chapter 9. The atoms have rotational energy just like a disk rolling down a ramp. Okay, heat is positive when the system gains heat. When you add heat to a system, that's going to be called positive, and when heat leaves the system, that's going to be called negative. These conventions, when I add heat to a system, I can change the internal energy. I can add heat to a bunch of atoms, and they'll all pick up a little bit of that heat. Each one will pick up a little bit of that heat in form of its kinetic energy. If a system does work on its surroundings and there's no heat flow, then the change in if the system expands and pushes against the environment, then that's system does work on its surroundings, then that work has to come, and there's no heat flow, that work has to come at the expense of the internal energy. The internal energy has to go down. The energy that did that work has to come from somewhere, and it comes from the kinetic energy of all the atoms. So if it does positive work, the change in internal energy is negative, it goes down. Okay. The first law of thermodynamics. So if the system changes due to heat and work, then the change in internal energy is Q minus W. I don't usually think of the equation like this. I think of the equation as Q equals delta U plus W, which you see is the same equation. I just moved the W to the other side. But this is the way I like to think about it. If I add some heat to a system, there's two things it can do. It has to go somewhere. It can change the internal energy. That is, the heat can go into changing the amount of kinetic energy of all the atoms, or it can do work. So if I dump 200 joules of heat into a system, a gas for instance, some of it's going to go into increasing the temperature, and some of it's going to go into doing work if the gas expands. So these symbols are not universal. Some people use capital E here for energy, internal energy. Not an unreasonable thing. Even worse, chemists in particular use work done on the system as positive and work done by the system as negative. So they have the opposite convention for W. And so their first law of thermodynamics will have a negative sign here. So what can I say? That's life. Thermodynamics is used extensively in biology, chemistry, every area of science, engineering, very much. Okay. In part 1 of the figure, the system gains 1,500 joules of heat and 2,200 joules of work is done by the system on its surroundings. What does the first law tell me about that? 1,500 joules of heat is equal to the change in internal energy plus the work done by the system on its surroundings, which is positive, 2,200 joules. This tells me how much the kinetic energy of the atoms in the system changed. Has this gas gotten hotter or colder? That'd be a good question. If this system were a gas, this gas is going to cool down because delta U, the amount of internal energy that it changed, is going to be negative. It's going to be a negative 700 joules, I think. So this gas is going to cool off, or this system is going to cool off, because it did more work than the amount of heat that you added. Okay, in part B, the system also gains, but 2,200 joules of work is done on the system. They have little schematics of this over here. So 1,500 joules, Q, is equal to delta U plus W. Oh, no, minus W. It's 2,200 joules of work is done on the system. That's negative for us. That would be positive for a chemist. Anyway, what happens to this system? This system heats up like crazy because I'm going to add 2,200 to both sides to find the change in internal energy. So I'm going to get 3,700 joules. So this system is going to heat up. This system is going to cool off. This is hotter. This is colder system. Okay, so that's the kind of thing that the first law tells us. An ideal gas. Okay, we have a formula for the internal energy of an ideal gas. This is an ideal monatomic gas. As I said, if they're diatomic molecules and they can rotate, then they have more energy at a certain temperature than if they could just fly around, colliding with walls and one another, for instance. Anyway, this is 3/2 nR. Okay. The temperature of 3 moles of a monatomic gas is reduced from 540 Kelvin. Remember, this has always got to be absolute temperature. If you see T in any scientific formula, then it's got to be kelvins. If you see a delta T, well, centigrade degrees are the same size as Kelvin degrees. So a delta T, it doesn't matter if you're talking about centigrade or Kelvin. But if you see a capital T in a formula by itself, no delta T, no change in temperature, then it's got to be kelvins. And that's true here. And it's also true in perv-nert. Absolute temperature. Okay, find the change in internal energy done by the gas. The temperature of 3 moles is reduced from that to that as 5,500 joules of heat flows into the gas. So Q is equal to, heat is added to the gas, so it's equal to 5,500 joules. Delta U, I got a formula for U if this system is an ideal gas. In the last example, they didn't say, it didn't matter what the system was. In part A, it's going to heat up, and in part B, it's going to cool down, no matter what the system is. In this case, we have a formula for internal energy, thanks to Ludwig Boltzmann. So this is 3/2 N, that's 3 moles, R, which is 8.314 joules per mole Kelvin times, I'm going to take the final temperature and put it here, and the initial temperature and put it there, and that's just going to, all these three things would be the same initially and finally. So I'm just going to have the difference in the temperatures here, reduced from this to this. So the final temperature is 350 Kelvin, and the initial temperature is 540 Kelvin. The change in anything is the final minus the initial. This is T final minus T initial. This gas cooled down, so it cooled down, so there's less energy stored in it than before. And so this is a big program. Let me grab my calculator for this. Turn it on. And I'll take 3/2, which is 1.5, times 3 times 8.314, parentheses, times, parentheses, and then 350 minus 540. If I got all my numbers straight. My dyslexia is not acting up today, I hope. I get minus 7108 joules. Moles cancel. Kelvins cancel. And find the work done by the gas. Well, Q equals, as I said, that's the way I remember the first law. And so Q is 5,500 joules. Delta U is minus 7108 joules. And this gas did a lot of work for us. So the work is just add 7108 to both sides, or add 5500 to that. Oh no, I got some negative on my calculator. So 5500 plus 7108. So this gas did us a lot of work. 12,608 joules. You know, if this was a steam engine, that'd be 12,608 joules of work we wouldn't have had to do. Lifting a weight or pushing our car, pushing a locomotive. All engines that do work for us work with the same principle. They take heat from somewhere. In the case of your automobile, it's heat from burning gasoline. And they turn that using gases. In the case of automobile engine, it's exploding gasoline in a cylinder that pushes a piston. They use that heat to generate work. And then usually they have to exhaust heat also. So gases can undergo three kinds of processes if you move them slowly. Moving a gas slowly through a process, that is, a process is something that does work or has heat absorbed in it, and or the internal energy changes. It's a change in anything Q, delta U, or W. It's called a process. A quasi-static process is one that takes place at each step, each little increment of the process. The temperature changes slowly, not quickly. So there's three kinds of processes that a gas can undergo. And we'll be talking about these throughout the chapter. Isobaric means that the gas will either absorb heat or do work at a constant pressure. Bar, barometer, means pressure. Isobaric. Isochoric is a process that takes place at constant volume. Put a gas into a fixed volume and add heat to it. Its internal energy will change. That's a process that's taking place at constant volume. Isothermal is a process that takes place at a constant temperature, as it sounds like from its name. And adiabatic, which doesn't have the prefix iso, it's too bad. Adiabatic is a process where no heat flows in or out of the system. Okay. So we'll be talking about these four processes throughout. How would I make a constant pressure process? Well, suppose I had a cylinder here and with a piston in it. And suppose I had a weight sitting on that piston. Here's a weight, mg. And here's a gas in here. That piston can move up and down. So if I put heat into this gas, Q, this piston will rise. It'll lift up that weight, but the pressure will stay constant because the volume will expand and the pressure will stay constant. How would I do a constant volume process for a gas? Well, I just put the gas into a closed volume, a sphere for instance, or a sphere. This could also be a balloon. I was just thinking, if you had a balloon where the stretch changes a little bit, but if as you blow up the balloon, it gets harder and harder to blow up. But for small little expansions of the balloon, the pressure would remain constant. If you had a rigid sphere, a ball, and filled it with gas and added heat, the temperature would go up because the heat couldn't go into doing any work. Here, the heat goes into doing work, lifting this piston, and also changing the internal energy of the gas. Here, all the heat goes into changing internal energy. How would you do an isothermal? Now, that's a little bit harder to describe. If you added heat to a gas and you let it expand in such a way that the temperature didn't change, then for an isothermal process, the change in internal energy of the gas would be zero. Here, for a constant volume process, there's no expansion of the gas and the work would be zero. For this process, the work is, if you add heat to the gas, the work is positive and the change in internal energy is also positive. And for a no transfer of heat, Q is equal to 0. Okay. So that kind of characterizes, in terms of W, delta U, and Q, what those three processes mean. All right. For an isobaric process is one that occurs at constant pressure. Well, here they have an example of what I just said. Here they have a movable piston with a weight sitting on it. And the volume is, when you add heat by heating this thing up, the volume is going to expand, and this little device here is going to lift this piston for us. Oh, very nice. It's going to do some positive work. Well, the force that the pressure, remember, we'll use capital P for pressure. The force the pressure exerts is equal to the pressure times the area. And if this is, I don't know what symbol that is, I can't read it. It's S, that's the distance. The work is equal to the force, the pressure, times the area times the distance. Well, this area times this height, S, is the volume, the change in volume of this gas. So this is equal to P times the change in volume. So that's the formula for the work done in an isobaric process. That formula only works for isobaric processes. 1 gram of water is placed in a cylinder and the pressure is maintained at this pressure. That's about 2 atmospheres. The temperature of the water is raised by 31 degrees Celsius and the water in the liquid phase is in the liquid phase and expands this. You know, when you add heat to a solid, there's not much expansion going on, not much work being done. When you add it to a gas, there's a lot of expansion going on and a lot of work being done. That's why we use gases, most commonly steam, by the way, still. More work is done by steam, the water vapor, than any other working vapor in the world, by far, and that will never change because we know a lot about steam. Anyway, find the work done and the change in internal energy. Okay, the work done is, here's the change in volume. So the work done is the pressure times the change in volume. Easy. Pressure is 2 times 10 to the 5th. Now, what is a Pascal? That is a Newton per meter squared. Cool. And what is the change in volume? 1.0 times 10 to the minus 8th. Meters cubed. So how much work does this, see this is not a good system for doing work because it's liquid water. We don't use liquid water to do work very much. We use vaporized water. And so this isn't going to do much work for us. It's going to do 2 times 10 to the minus 3. This meter squared cancels with these meters times meters times meters there and gives me a Newton meter. Yay, the magic of our system of units. It's logically consistent. 10 to the minus 3 is a milli, and a Newton times a meter is a joule. 2 millijoules. That's not going to get you anywhere. Find the work done and the change in internal energy. How would I find the change in internal energy? Oh boy. I need, well, what do I need? I got the first law here. Q equals delta U plus W. How am I going to find Q? I think Q is really a lot of joules. Because Q is going to be so much that this 2 millijoules is going to be negligible, actually, in this problem. But we had a formula last chapter. Q equals mc delta T. So the water went up 31 degrees centigrade. And do they tell me how much water this is? 1 gram of water. 1 gram. So we have to change that to kilograms. That's 0.001 kilograms. And C is a monster number for water. It's 4186 joules per kilogram degrees C. And delta T is 31 degrees C. So this is a monster amount of joules compared to 2 millijoules. So the change in internal energy is going to go up by a lot. And this 2 millijoules won't matter. So what is that number? Well, this is 4.186 when I multiply it by 0.001. 4.186 times 31. $129, let's say 130 joules. You see, when I add 0.002 joules to 130 joules, I'm just going to get the change in internal energy is equal to 130 joules. All right. So here's a way to represent an isobaric process. And when we're dealing with gases, we like to make when we describe a process, we like to keep track of the pressure and the volume of the gas. So we make a graph with pressure on the vertical axis and volume on the horizontal axis. And this is going to be generically called a PV diagram. Nice. P versus V, Y versus X. So a process would be a graph on this diagram. And here's a process that's taking place at constant pressure. You see the pressure here is constant, and you're going from some initial volume to some final volume. So the work, we already had this, the work is equal to P, the pressure that it takes place at, times Vf minus Vi, the change in volume. That turns out to be the area of this rectangle here. This is the one side of the rectangle, Vf minus Vi, and P is the other side of the rectangle. So this area under the PV diagram is equal to the work, and that's true in general. This is the work done by the gas. If this process went the other direction and the gas was being compressed to a smaller volume, then this would be a negative work and the gas would be cooling off or heating up. In this case, the gas is cooling off. It's expanding. In the other case, when you're compressing it, the gas will be heating up. Okay, so a constant volume process. What does that look like? Well, here's my pressure axis. And here is my volume axis. And I go at constant volume, that's what caloric means. Yeah, constant volume. That process is going to be a vertical line here. Notice there's no area under that curve, so the work is equal to 0 for a constant volume process. All right. So if I increase the pressure of a gas, holding its volume constant, no work is done. And the increase the pressure and keep the volume constant. What will happen to the temperature? The temperature will go up. In this case, Q is greater than 0. So heat is being added to this gas in order to make the pressure go up. Okay. So the area under the curve represents the work. Determine the work for the process in which the pressure, volume, and temperature of the gas are changed along the straight line in the figure. Okay, so the work is equal to the area underneath this whole curve. So I'm going to break this curve up into a rectangle and a triangle. Can I see what's going on here? Each little square here is a work of this times this, the area of that little square. So I'll call that, I'll call it little w. The work encompassed in a little square on this diagram is 2 times 10 to the 5th. Once again, a Pascal times a meter cubed is a joule. So times 1 times 10 to the minus 4. I can do that in my head. So each little square has an amount of work of 2 times 10 to the 1, 20 joules. Alright, so can I find out how many little squares are in this? 1, 2, 3, 4, 5, 6, 7. Well, this little piece is missing here, but it's kind of made up there. So that's 8. And this little piece is missing here, but it's kind of made up there. So that's 9. So it looks to me like I got about 9 little squares in there. And 9 times 20 is 180 joules. Okay. Alright, that gets us started. That's a good start on Chapter 15. We're going to have one more assignment, one more homework assignment for the semester. A couple problems on Chapter 15. There'll be a couple problems on a problem from Chapter 15 on the final. It will not be on the last test. You can see what chapters are on the last test on this Thursday by looking at the practice test. That covers the same chapters as the regular test. And that's all for now. Have a good Monday.